get started. I don't think everyone is here, is he? Is everyone here? Okay. Well, anyway, we'll start summarizing a little bit some of the things we have seen yesterday before we move into the multidimensional integrals. So let's recap. So start with this integral that describes a partition function of a one-dimensional system where this is the energy of a particle at a position x. So the cost, that particle, is in some potential. It's like an harmonic potential, plus some small anharmonic term, gx to the 4. And suppose we are computing it in an expansion at small coupling g, which is called perturbation theory. Yes?
I'm sorry, shouldn't you turn on the...
Yeah, probably. That's a good point. Thanks. So suppose we want to compute it as an expansion in g. So exponential of g is 1 plus g squared over 2 factorial plus g cubed over 3 factorial, dot, dot, dot. So we start expanding this quantity, and we get 1 plus g times whatever is in the exponent plus g squared over 2 factorial times whatever is in the exponent plus dot, dot, dot. Now, each expectation value of x to the n is just n minus 1 double factorial when n is even and 0 when n is odd. So immediately, this number gives 1 over 8. This number gives 105 over this number here, and so on. So we can just compute it. But more than that, we were giving a graphical interpretation. We were saying, oh, this 1 over 8, I want to associate to this graph where I have a 4-point vertex. And the 1 over 8 is just a symmetry factor. It's just how many transformations are there that leave this vertex invariant. And here I can swap the 2 lines in the bottom, swap the 2 lines in the top, or swap top and bottom. So 2 times 2 times 2 is 8. What about this 108? This 108, we break it into 9 plus 72 plus 24, these 3 graphs that we saw. We divide by that factor over there. We get this, 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 which are the right symmetry factors. Okay? So let's pick one at random. This one. Okay, the middle one. So 2 to the cube times 2. So let's see. It's 2, 2, 2, and then just flip the graph left and right. An extra 2. Okay? You can check the other ones. It also works. And then what do we see? We see that this model of a one-dimensional particle in a line in a potential is the sum over graphs with n vertices, each of valency 4. There is a counting parameter to tell how many vertices there are, g to the n. And then we just divide by the analog of the 1 over n factorial for indistinguishable particles, which is now 1 over the symmetry that leaves the graph invariant. In the same way that the n factorial was the symmetry that leaves the configuration invariant if I just swap particles that are indistinguishable. Okay. By the way, often when we say I sum over graphs, g to the n, we often even omit this factor. Because it's understood that this factor should be there in the same way that when we sum over electrons in a partition function, there should be 1 over number of electrons factorial. And we sometimes also forget that term. And this was a definition of a partition function of a statistical mechanical model. We used the different z. And therefore, we had this duality between this curly z and this straight z. And furthermore, we also noticed that this z, which is like, as I said, a guess of graphs, because I have connected and disconnected, right? So this z is like summing over all possible graphs that can be connected or disconnected, whereby this blob, I mean a graph, right? So I don't know, a graph like this, for example, etc. Right? This is the quartic vertices here inside. Whereas here, when I exponentiate, these are just connected graphs. I just sum over graphs that have a single component. So it's more like the thermodynamics of a single blob versus thermodynamics of a guess of blobs. And we see that because they don't interact with each other, disconnected graphs don't talk to each other, studying a guess of graphs is just equally easy to studying just a single one and then just exponentiating. Okay? That's because there is no energy cost, no interaction of 2 graphs. They are disconnected, they are disconnected. Now, let me make a few comments, a couple of things that people asked me before. One is that these discrete graphs this problem of graphs are discrete. We have a given finite number of vertices, given finite number of lines, and so on. The motivation in the very beginning of the lecture, I was speaking about smooth random surfaces. So, of course, it's implicit in what I'm saying that if we want to get some smooth random surface, we have to consider many vertices and many edges and take what people call a continuum limit. So we look from far away, and then these graphs with many vertices and many edges would look like a smooth surface. As I said, like a computer game. A computer game, from far away, the characters look smooth, but if you zoom in, it's a bunch of triangles. Okay, so it's exactly the same thing. So that's comment number one. Comment number two, people ask me, what's the physical meaning of this G? So again, maybe it's obvious, but let me emphasize. So what's the physical meaning? So here, it's pretty clear, right? So here we just have a potential, and if you give me any potential that is even, well, the first approximation it's a parabola, then there is some anharmonicity, right? So this is just a way of parameterizing an even potential, right? So an even potential is always a parabola plus some small deformation plus some g prime times x to the 8 plus dot, 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 right? This is just the most general expansion of a potential that is symmetric, right? So that's just a parameterization of my energy functional. I could actually take this g prime x to the 8 here and add this term here. And then when I expand, I would have vertices that have valency not only 4, but also 8. Actually, why 8? 6. The next term is 6. So I could get, and then I'd have valency 4 and valency 6 in my graphs, right? And I would just look at the power here and here to see how many of each type I have when I expand down. Is it clear? What about the physical meaning in this statistical mechanical sense? Well, written like this, it might not be immediately obvious if I tell you that G is a chemical potential for the growth of these graphs. But it becomes obvious if you just define G as e to the minus the inverse temperature times the chemical potential. Because then what is G to the n? G to the n is just e to the minus beta mu n. So we see that beta mu is like the energy per vertex. It's like it costs some energy to put a vertex. So if G is very small, means that beta mu is very large, it's very costly to grow a graph. Then the graphs that dominate a partition function are graphs with very small number of vertices. If on the other hand, beta mu is very close to 0, which means what in terms of temperature? Very high temperature. Then G is very close to 1, and these graphs are not suppressed, and all graphs are important, which is what we expect. If the temperature is very high, we produce all sizes of graphs. If the temperature is very low, we stay with the smallest graphs that have smaller energy, right? So the meaning of G is a counting parameter for graphs or a chemical potential associated to the number of vertices, right? So G has a meaning here of a chemical potential. Okay, let's see another example. Suppose I replace the x to the 4 over 4 factorial by x cubed over 3 factorial. Just so that we see another example. Well, we expand, we get 1 plus x cubed squared plus dot, dot, dot. What is the average of x cubed? 0. So we start to get 1 plus 0, average of x to the 6, 5 double factorial. 5 double factorial over 3 factorial squared, 2 factorial, right? Is this clear? And now I'm telling you that this number is the same as this. It's 1 over 8 plus 1 over 12. Okay? So can you guess which graphs would correspond to these two? It's a bit hard to describe graphs by words, but it's not so hard. So how many vertices should they have, these graphs? 2 vertices. So what's the valency of these vertices? Yeah, they are cubic vertices. And so there are not that many ways of making graphs with 2 vertices. There are 2 options, right? One is all lines from 1 connect to all. Which one is this, the first or the second? Who thinks it's the second? No one. Who thinks it's the first? Yeah, it's the first. So let me draw. So this is, so why is it the first? Because what's the symmetry? I can permute the lines, that's 3 factorial, and I can swap left and right, that's the 2. Right? So that's the symmetry factor for this graph. What's the other graph? So if they don't talk all to each other, what can they do? They can, exactly, I've seen you draw. They can do like this. And let's see that the symmetry factor is right. Is this correct? Indeed, I have 2 for the left, 2 for the right, and then I can swap left and right, so it's another 2. Okay, so it works nicely. So we get exactly the same thing with valency 3. Okay. Now we are moving to multidimensional integrals, where instead of having a parameter alpha, which in that case is actually 1, now we have a matrix, a symmetric matrix. And instead of having a source, which is a number, now we have a source, which is a vector. And we already anticipated a few results, this and this, that this partition function is equal to the partition function without source times this very important exponential. And the partition function without source, it's a normalization. It's not so important for these lectures, but it actually can also be computed, and it's given by this determinant. These 2 results we didn't derive. We are going to derive now.
When you were drawing those graphs, a question that I had tomorrow was,
Yesterday.
for example, when I was drawing the third order graphs, how do I know if I already draw all possible distinct graphs that I can?
So the question is, when I'm drawing these graphs, let me take the opportunity to mention that these graphs, they are what physicists call Feynman graphs. And the question is, how am I sure that I didn't forget a graph? For example, I could think that this is the only graph that there can be. I forgot that there was this one here, right? And this becomes especially hard when I have many terms, like cubic terms and so on, right? So what could be a recipe in this, if I go, say, to the next term? So the next term, g cubed is 0, but g to the 4, right? G to the 4, there are many graphs I could draw, right? So how could I, in this case, in this simple case, how could I know? Well, it's easy. I would draw all the graphs, and for each graph, I put the corresponding symmetry factor, right? So that's okay, that's easy. But I don't know the number, I don't know how many types of graphs there are, but the very total is very easy, because the very total is just average of x to the 12. That's just 11 double factorial. So I know that when I add them all up, I know the analog of this. This result I know. Instead of 5, it will be, 9 double factorial over. So I know this full result, right? In other words, the total number, when I add everything up, it is just how many ways there are of contracting, how many pairs there are. It's always n minus 1 double factorial, and that's it. And I have to break that number, like I did here, into subgroups. So if the subgroups add up to this number that I always know, I know that I didn't forget graphs. Okay? So the point is that here, if I add up 9 plus 72, I know it doesn't add up, I'm missing some graph. Then I put this, it already adds up to 105, I know I didn't forget. Right? So you do first this without the symmetry factors, and without the symmetry factors, you know what they must add up to. Is it clear? But another answer is that you use a computer. It's true, because these ones, everyone does by hand, these first ones, because they're easy. But no one is doing 5th order by hand. People use computers. And, you code. It's not like it's a black box. You know how to do. It's mechanic, right? So you should teach the computer to do. And you teach the computer, and the computer doesn't forget. Okay? Okay. So let's establish those identities there. So let's start by the first one, where we show the first equality, that z of j over z of 0 is this exponential. Remember, how did we do it when j was a number and a was a number? We completed a square, right? And after we complete the square, the one part was just the original Gaussian, and whatever remains was the result. So let's do the same thing. So we have to complete the square. So we have to do the following. We have minus 1/2 x transpose dot A dot x plus j dot x. This is the result we have. Okay. So you understand what this means, right? Vector, we have x1, j1, x1, j2, x2, and so on. I don't need to put transposes in this particular one, right? Here, let me keep it. And now I want to write this. The goal is to write this as minus 1/2. I shift x now, and I write this as x minus some b transpose dot A dot x plus, sorry, minus. I shift minus b. Right? So I want to shift this. And I want to say that the x squared term, of course, works. The term without x is not there. So whatever this b is, I will need to add plus b transpose dot A dot b over 2, right? If this b exists. And now I want to tune b such that this term comes out, right? This one comes out correctly for sure. There's no constant because I canceled it, so I need to make sure that this term comes out. So the goal, this is the goal, is to write that term to complete the square into this, right? Because if I complete the square into this, then the next step, right, this is a vector. I call this a new vector y, right? And then integration over x is integration over y, and I get back z of 0 times that part, right? So then we are good. That's like the shift. Okay, so what is b? So you see that b, the result you get, you should use the fact that A is symmetric, and you get, indeed, if I open up, I get minus 1/2, let's write carefully, x transpose dot A dot x. Okay. The term with b squared cancels that term, and then the term with x, let's do, say, this one, gives minus, well, let me write the result, and then we see if we agree. It gives x dot A dot b. Right? So x, okay, x transpose if you want, dot A dot b, that's this term. And there is another one where you take x dot A dot b transpose, but A is symmetric, so putting x and b here or b and x here, it's the same, so it just gives a factor of 2. Okay? So here, in writing this and not two terms, I'm using the symmetry of A. Symmetry of A tells me that A has two indices. I can contract x and b on left, right, or the opposite, and it's the same thing. So the two terms give the same thing. Okay? So what should be in order for this to agree with this expression? Sorry? So what do I want? I want this, right? So I want A, matrix A times vector B to be vector J, right? So it's easy. We just take B to be the inverse of the matrix A times vector J. Right? When you plug here, A times A inverse disappears, and I get just vector J. And then it works. It gives x transpose dot J, which is x dot J, right? It's the same thing. This is just vectors and so on. I can remove the transpose, not to confuse people. Is it okay? So if I plug here B, A minus 1 J, I get back to that line, right? And so and then if I plug this here, then this part is what? Well, let's transpose. So I get J transpose, right? The transpose flips the order times A minus 1 transpose dot A minus 1 dot J, everything over 2. Transpose or not transpose here is irrelevant because A is symmetric, so A minus 1, the transpose doesn't matter. And I have a minus 1 dot a is identity. 1a minus 1 survives, and therefore we reproduce the result we want. Yeah? So this part is indeed just equal to j dot a minus 1 dot j divided by 2. Okay? In other words, it's not more complicated than the previous case, except that you have to be careful that completing squares with vectors, you have to be a bit more careful. The analog of the 1 over alpha, that when you expand cancels the alpha outside, now it's an inverse of a matrix. Okay? So you just need to, it's just slightly more sophisticated, but it's the same thing. Okay? So let's just, again, just because, to make sure everyone followed. So because of this, we conclude that z was equal to integral dx1 dxn, but this is equal to dy1 dyn, where y and x differ by that shift. It's just a shift of the variables. They are all integrated from minus infinity to plus infinity. Exponential of minus y dot a dot y over 2, right? Where y is x plus some shift. The shift we just computed, but it doesn't matter because this integral here is by definition, I didn't finish writing, I'm still going to write, but this definition is by definition z of 0, right? And then what remains is exponential of j dot a minus 1 dot j divided by 2. Right? And therefore, we establish the result we want. Z is equal to z without source times this nice exponential. Okay. We did not prove yet that z of 0 is this determinant. And I'll do it a bit later. It's very easy to do, but for what we want, which is to compute expectation values of x1 and so on, we don't need it, so let's postpone a little bit. Okay. So again, this reduces when n equal to 1, when there is one component, to exponential of j square over 2 alpha, which was the result we saw yesterday. Right? N is just a number j square, and the inverse of a is just 1 over a. Right? But otherwise, it's this more interesting result. And now, we can go and compute expectation values. Because now we have the generating function. Now that we know that z of j over z of 0 is just this simple exponential, then it means that any expectation value in this multidimensional Gaussian integral, expectation value of x I1 dot 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 x In, right, is just derivative with respect to I1 dot 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 derivative with respect to In, right, of z of j over z of 0. What is z of j over z of 0? Is this exponential there, right? I plug this exponential there. And again, this exponential, I want to take, what have I done here? I forgot. There is a j, right? You agree? Derivative with respect to j index I1, right? Derivative with respect to j index In. Is it okay, everyone? And then after taking the derivatives, I will put j to 0, right? Because each derivative brings down an x, right, from the original definition. So it's clear that this is what I should do, right? I just take the derivative with respect to j to bring down the x's, and then I put j to 0, because j was just there to make so that I could take these derivatives. Yes?
Why not the y transpose in here?
Y transpose, or, sorry, what are you asking? Where? Here?
Yeah.
Like the same thing, right? I mean, whatever. You understand? A dot y is a vector. And this is vector contracted with this vector. So I don't know. In components, it's y, I, a minus 1 component ij, yj, with sum over repeated indices. Right? So now, if you want, I don't know. Okay, and now we want to take these derivatives of that exponential, but that exponential, as before, there are some terms that have too few j's when I expand the exponential. Then there is the one that has exactly the right amount. Let me say that I have 2n, because if n is not even, it will be 0. So let's put 2n here. And then the interesting one here is 1 over 2 to the n factorial, right, when I expand that. And then I have j dot a minus 1 dot j. Again, if you want, you can put a transpose in this one, to the power n plus dot dot dot, where this dot 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 are too many j's. Okay. And in this case, because I take exactly 2j derivatives, I don't even need to put j equals 0 because the derivatives will get rid of all the j's. But you can put j equals 0. Okay? So we just need to take the derivative of this term here, right? The derivative of this term here, which we could write like this. We could say that this is j, let's say there are 2n of them, so let me call j index k1, j index k2, j index k3, dot, 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 j index k2n. And then the indices are contracted, a minus 1 contracted with index k1, k2, dot, 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 all the way to a minus 1 contracted with index kn minus 1, k2n. k2n minus 1, k2n. Right? That's just a way of writing explicitly that term over there. Okay, so before we act with this general derivative on this expression, that you will see that you will remove all the j's, right, from this expression and leave only the a minus 1. So we see that this correlation, we already see this is a bunch of a minus 1s. Right? We just take all the derivative, get rid of all the j's, we get some a minus 1s, and we'll be rigorous about what does this mean. But for now, let's observe what is the simplest case where I have x, I, x, k. Well, if I just have 2, then here I just want to have 2 j's. Here I have 2, 1, 1, so 2 and 1. N is equal to 1, right? So what happens with the derivatives when I act with these two derivatives? They just remove the 2 j's, and the derivative can act on the first or second j, so there is a factor of 2 that cancels this factor of 2. Right? So you agree that this quantity is equal to the inverse of my matrix component ik. Okay? Now, in pictures, sometimes we draw a picture like this. We say that I have I have k, and I'm computing a correlation factor of these two guys, and I join them. This is just a cartoon. And we say that we think of this as expectation value of point I and point k. We draw like this, and say that the outcome of computing this is connecting them I and k, and the connection is this inverse matrix that is called a propagator. Propagator, it's like propagating from I to k, connects I and k. Right? So we use this name, propagator, it's just a name, but you can think that it propagates from I to k. It connects I and k. Now, this is just a cartoon. You are not obliged to, the formula is the formula. The pictures then is just definitions. Just, I like them, but you don't need to use them, right, of course. Okay. So now that we know the two-point function, in particular, you see that these objects here, a minus 1, if I want, I can replace each a minus 1 by a two-point function, by an expectation value of 2x's, right? Because a minus 1 is the expectation value of xk1, xk2. And this is the expectation value of xk2n, xk2n. Right? So we can also say it's a bunch of a's or a bunch of two-point functions xi, xk. Because each a minus 1 is a two-point function. Now, the precise formula for this bunch is what's called Wick's theorem. Okay, so let's write the precise formula now. Okay. So this is a very important theorem. It's called Wick theorem. Okay. And Wick's theorem says that if I have expectation value of x I1 dot 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 x I k, okay, this k is 2n, otherwise the result is 0, right? That this is equal to the following. So let's look here. What is happening? I take this derivative and I act and I remove all these j's, right? So let's say index I1 and I2. What happens to index I1 and I2? Where are they? Well, depends. If they act on these first two guys, this a minus 1 will have indices I1 and I2 after they act, right? But if they act on different j's, one index will be in one matrix, the other will be in the other matrix, right? So each matrix A can have will have two indices that are a pair of the outer indices. Okay? So the result is that I should take these indices and I should sum over all possible pairs, all ways of pairing the indices, right? So let's try to introduce some notation. It's actually a bit subtle to write this formula in a rigorous way. In cartoons, it's very easy. So let me be rigorous about these pairs in a second. And then we associate this in pairs. And for each choice of pairs, I just multiply a minus 1 with the first index. Let me call it from a equal 1 up to k over 2, which is n. A j a k a, which is equal, if you want, to expectation value of x j a x k a. Where, what is this j and k? What have I done? I had a bunch of indices, I1 up to ik, and I broke them down into pairs. I said that I distribute these indices into the pair with indices j1, k1, etc., j n, kn. Okay? And if you think a little bit, if you don't want to have overcounting, you should say that ja is smaller than ka, for example, right? Because you don't want to overcount, counting the same thing twice. And you can also order the ja plus 1 bigger than ja. If you do these two things, this avoids overcounting. But this is a complicated way to make sure that this formula is rigorous, to make sure that this is good. This is just overcounting. you can think, to avoid overcounting, you can think of different ways of writing, but the sum over pairs should be clear, and let's work out one example. And when you see this example, you will understand immediately any number of x's, and it will be clear what you should do. Let's work out the case with a 4. You see that if you have 2, then there's only one pair, it's done, right? Then it's just the single pair, I just contract, and that's it. So the simplest case, the next to interesting case, is the case where I have xi, xj, xk, xl. Okay? And now what's the claim? The claim is that I think of these guys as I, j, k, and l, and I form pairs. All possible pairs. So what's one pair? You see the usefulness of that picture. I've just drawn these lines to indicate these guys made pairs. This is one pair. Okay? This is one option. So this line that contracts is called a weak contraction. And then this term, for example, this first term here, sorry, this is equal, and now I'm going to, this would be the first term, would be I just contract I with j, so I get xi, xj, and then the other xk, xl. Right? That's one pair, I with j, k with l. Do you agree? So what are the other options? Plus, what's the other option? One pair is I with j, k with l. What's the other possibility? I with k, right? So then there is the possibility xi, xk, xj, xl, which in pictures, it's very easy. We just contract now this guy and this guy. And what's the last one? Now I connects with the last one, I with L, J with K, right? Which would be this. Right? Where each of them, I chose to write it in this way. This is nothing but A minus 1 IL. Right? How many terms are there in here? 3, and this 3 is just take the first guy, choose how many options there are, take the next guy, choose how many options there are. The fact that there are 3, you see, it's just these 3 double factorial terms. Right? In general, that's how many terms there should be. If I have 2n fields, I should get 2n minus 1 double factorial such terms in the weak contractions. So in other words, this fancy thing, the way we say, this is a sum over the 2n minus 1 double factorial weak contractions. Okay, so this is equally clear as this. Here, I'm writing a mathematical formula to make sure that I don't overcount. Again, I have to say that I take the indices, break them into pairs, make sure that you don't overcount, so order them in some given canonical way. It looks complicated, but in pictures it's very simple. Just draw the various operators and contract them in all possible pairs. For example, let's make a small parenthesis and go back to n equal to the case with one component. Then we add that expectation value of x to the 8 or x to the 2n, which is x, 2n times, right? That I can think of this as just a bunch of x's. Right? So they are ready to be contracted. Right? And then I just go here, and I choose this guy to contract with this one, this with this one, this with this one. And there are how many options? Well, there are all options give the same thing because there's only one type of propagator. This propagator here is now expectation value of x, which is just equal to 1. So all graphs give the same, give 1 times 1 times 1, which is 1. And there are 2n minus 1 double factorial graphs. Right? And so we reproduce the same 2n minus 1 with Week's theorem, where I think that I compute x to the 2n by drawing 2n x's and then we contracting them in all possible ways. Okay. Let's see another application in n equals 1 that I wanted to mention is that suppose I have z defined by integral dx over square root of 2 pi, to normalize it to 1, exponential of minus x squared over 2 plus the sum of gk x to the k over k factorial. Let's say that k is bigger or equal than 3. And this is equal to the sum over all possible graphs, because now I have all possible valencies, cubic, quartic, everything. Right? And now what should I write? So let's see. So there will be 1 over the symmetry factor of the graph. But then what do I write replacing g to the n? Sorry? Well, gk, but what is k? There's no k here. Product, so it needs to be a product from k equal to 3 all the way to infinity. Right? G3 to what power? To the power what? What is nk? So someone is proposing, let's write gk. Instead of gk, g to the power n, let's write gk to the power nk. That's correct, but we have to tell me what nk is. What is nk? Where I sum over all graphs, let's put here, with nk vertices of valency k. Right? So they can have n3 vertices of valency 3, n4 of valency 4, n5 of valency 5, and so on. And then this would be the power they would come. So let's just check this. So you see that this is now all graphs. So we have done quartic and cubic. Now we did all of them. And that's it, actually. But the rest, I will leave. There is an exercise here that I think you are encouraged to see. Okay. Well, let me maybe ask already as an exercise. Will there be a term with just, so there will be, so this is equal to 1 plus any monomial, right? Plus any possible monomial. For example, just G3, but just G3 is just a cubic vertex. It's not possible, right? Just a cubic vertex, I cannot make a graph. So G3 comes with 0, right? Plus any other monomial. For example, what about G3 times G4? Is it possible to make a vertex, to make a graph with a cubic vertex and a quartic vertex? No, this one is also 0. So many terms are 0. Right? Some are possible, some are not possible. So in the exercise, for example, you are asked to describe which ones are possible. So it's a nice exercise to think a little bit about graphs, to think a bit. So yeah. So what should be the basic rule? Yeah. In total, you better have an even number of, each edge connects to two vertices, so the number of lines getting out of vertices better be an even number. Right? Okay, good. So that's part of the exercise. Now, we can also do something very cool. So let me define a partition function. Let's call this the red-blue partition function. And I will define it as follows. I will say that this is a sum over all graphs, and now I'm going to draw the type of graphs that contribute. Well, I don't have actually, I can call it, okay. So let's suppose that I have two types of vertices now. That can be this one, let me call it the red one. And then this one will be the blue one. They are cubic vertices. And these ones as well. So this is now a more interesting graph problem, where the rule can be, can you see if I write like this? Is this visible, or it's better if I use white? It's okay? Where the rule is that blue connects with red, but not with the same color. So we say that the only, can you still read for sure? Okay. The only contraction that we have, the only way, the only rule, the only thing we allow is that we connect two colors that are different. Okay? So it's like positive, negative. They connect, but same color they don't connect, right? Like some cable, right? A USB cable. It connects from red to blue and always from red to blue, not from blue to blue, right? Like female, male ends of the cable. Okay, so it means that I have to draw all possible graphs like this. For example, this is one possibility. This guy could couple here. Let's draw an example. This guy could go here. This guy could go here. This guy could go here. This guy here. This guy here. This guy here. And I must have some line missing. Yeah, this one here. Okay. So this is an example of one such graph. This is fully connected, but there will be also disconnected ones and so on. All right? So is this definition clear for everyone? Just sum over all possible graphs. Notice that I drew as many yellows as blue. Is this needed? Yes, right? Because if each yellow goes to a blue, I better draw all vertices, right? So this, for example, will only have terms where if I have an associated coupling G red, and if there is an associated coupling G blue, then this term, for example, would be proportional to G red cube times G blue cube, and there is no term which comes with different powers. Okay, so now suppose we want to write an integral that solves this problem of combinatorics, right? We can now start, put in a computer first 20 terms, but it's hard to go on. I want to write directly an integral that says this is the solution to this combinatorical problem, right? So how could we do it? So again, imagine there was no story with colors. They were all the same. We know it's the cubic integral, right? That's the one we started in the beginning of the lecture. I just write Gaussian integral and cubic interaction, right? But we want to do this one. It's more interesting. It's not just cubic. There are two colors, and they connect to each other, but they don't self-connect. How would I do this? Sorry? Multidimensional is a great idea. So we want to use a multidimensional integral, because what's a multidimensional integral? It also, when I expand, it instructs contract in all possible ways. But now we have this tool that we can decide how things contract. We can say that x1 with x2 contracts in one way, but x1 with x1 and x2 with x2 contracts in different ways. It's just our choice of our matrix A, which is our propagator. Okay? So let me write the result, and then we'll see together why this is correct. But since the result is so beautiful, let's write it right down. So the claim is that this Z is equal to curly Z, that we can also put blue-red, which is defined as the integral dx dy over 2 pi. Now we are using two-dimensional version, n equals to 2 instead of n equals to 1. So instead of x, I have x and y. And the term would be exponential of minus x times y plus g red x cubed over 3 factorial plus g blue y cubed over 3 factorial. Okay? So this very simple two-dimensional integral solves this problem of combinatorics. Okay? So let's see why. And the reason is very simple. You see that here what we are doing is an n equals 2 multidimensional integral. Right? We are doing a multidimensional Gaussian integral where we are calling x1 and x2, we are calling it x and y, right? That's how the notation goes. And let's see, what are we using then for our x1, x2? Then we have our matrix A. Let's write it here explicitly. A11, A12, A21, A22, and then xy. Okay, x1, x2. Right? What matrix? So the kinetic term should be minus 1/2 of this, right? And apparently it gives x times y only, right? That's the quadratic term in the variables. So what is the matrix A that we are using? Sorry? 0, 1, 1, 0. Do you agree? It's the Pauli matrix sigma x, right? Then, indeed, so it looks like I'm using the matrix A to be just 0, 1, 1, 0. Then you see that when I contract with xy, it gives xy plus yx. Divide by 2, it just gives xy. But this matrix A, what does it mean? So we have to compute the inverse of the matrix A. But what's the inverse of the matrix A? It's the same in this case. So this matrix is also equal to its inverse. Right? This matrix is its inverse. If you multiply sigma x times sigma x, you get the identity. And that means that the expectation value of xx is the element a minus 1, 1, 1 is equal to 0. Expectation value of y with y is element 2, 2 is equal to 0. But expectation value of x, y, which is I minus 1, 1, 2, is equal to 1. Right? And so in pictures, it means that if for y I use the blue, if for y is white, if this is 2 whites, this is saying that there is no propagator between the two, right? Or if I want, let's put a dashed propagator and say it's equal to 0. If x is the red one, it says that there is no propagator between the two. So whenever I draw this weak contraction, this weight is 0, right? Or you could say there is propagator with weight 0. So whenever I draw these weak contractions, I get 0. But this weak contraction is equal to 1. Right? Yeah? So that means that when we compute, for example, we start with this integral. And let's write the first term that is non-zero. So let's see it a bit slower. So this is equal to 1 plus the first term. If I just take red or just blue, I get 0 by symmetry, right? So the first interesting term is just 1 red and 1 blue, right? So let's see. I expand, so I have 1 over 3 factorial. 3 factorial. That's from expanding both exponentials. Expectation value of x, 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 y, y, y. Yes?
I'm sorry, how did you find out that the first term is minus xy?
Sorry, yeah, I should have said more slowly. So you see that the way I would find out is going the opposite direction. This is what I want. I want to have these contractions. I want to say that the rules for my graph are such that I want to get 1, 0, 0. So that's what I knew. I knew that this was the matrix, the inverse of the matrix I wanted. Right? So then I want this inverse, but this inverse means the matrix A is this. I plug this matrix A, here is xy, I get this. So it starts from exactly the opposite direction, right? I just check that it works, but the way I would derive it is starting from what I want, which is this inverse to be just this. So let's see. So I have this. And what are the rules of the game? The rules of the game is now draw weak contractions, all possible weak contractions. So let's write one weak contraction. Let's use this notation for the weak contractions as before. One is this pair, and this pair. But what does this weak contraction give? 0, because x with x is 0. We said that x cannot contract with x. So what are the weak contractions? So this one is equal to 0, but not all weak contractions are 0, right? Let's see an example of one which is not 0. This x with this y, this x with this y, this x with this y, right? How many are there which are not 0? 3 factorial. Right? I take the first x and say, to which y do we want to go? That's 3. Second x, 2. Last x, 1. All right? So this result here, the full result of the Week's theorem, tells me that I have 3 factorial times the expectation value of xy times expectation xy times expectation xy. Right? Which is equal to just 1. Because we define it to xy is just 1, each of them. And so in total, what do we get here? 1 over 3 factorial. Right? 3 factorial and 1 over 3 factorial outside, 1 over 3 factorial. And what's the graph that corresponds to this? Well, this graph, as we said, we have the y's. The y's are the white ones. And we have the yellow one. And then we contract it. Let's use the red line to contract. Otherwise, it might. I don't know where the red line is. Where's the red chalk here? What symmetry factor should I put here? 3 factorial for permuting the lines. And someone is saying 2, but should he say 2? No, because they are not indistinguishable now. So now just 1 over 3 factorial. In the beginning of the lecture, there was an extra 2, not now. And indeed, we get 1 over 3 factorial. Right? It's just a permutation of the 3 lines, but no factor for indistinguishability. Okay? And we did. Why did it work before and not now? Because before, it was the same vertex brought down twice, so there was a 1 over 2 factorial from expanding that exponential. But now it's once this, so there is no 2 factorial coming down. So that's why technically it works. Right? So we just established this new configuration. Right? What would you do So so that's one example. Let's see another example. Suppose now I have three colors. So let me indicate them by A. A can couple to B. So, and let's suppose, okay, I have something. Let me see, what example did I choose? Okay, all quartic vertices. So suppose all vertices are quartic like this. And this A with C, A couples to the two neighbors, but not to itself. Okay, and I sum over such graphs. Right? For example, there could be a disconnected one, for example. Let's put here again, A, B, C. Right? So this is an example of, for example, that contains. Right? So how would we write down this matrix integral? Right? So I want to sum this, and I want to say that this is equal to Z, which is the integral. Let's just start writing. Let's not finish it, but let's write some of the ingredients, the important ones. So first of all, how many integrals would there be? Three, because now we have three types of particles. So we would have integral dx, dy, dz. Okay, some normalization here that we could work out. And then what would we write for the kinetic term? The kinetic term means the quadratic term. So someone is saying xy, xz, yz. That's not correct. Be careful. This was just xy by a coincidence that a minus 1 was equal to a. Right? The correct thing to write is exponential of minus 1/2. Let's write here the vector x, y, z. Here the vector x, y, z. And here I want to put a 3 by 3 matrix. Right? But it's easy to just say it's the inverse. And the inverse, I know very well what I want to get. What do I want to get? X talks to y and z, so 0, 1, 1. Y talks to x and z, 1, 0, 1. And z talks to x and y, 1, 1, 0. Right? Whatever this inverse is, this is guaranteed to give me the connections I want. That x talks to y and z, y to x and z, and so on, because this is what the elements are here. Right? So this is whatever, you just compute this inverse, and that's what you want to replace xy in this case. Right? And then there are some interactions, and the interactions would be plus some g, some coupling g, for example, of that type there, which of type A, so x to the 4 over 4 factorial, plus the same thing for y, plus the same thing for z. Okay, so it's actually, the full result is here. Okay, so all quartic vertices that can be of type A, B, or C. And now it's designed such that A couples to B, A couples with C, but A doesn't couple with A. Right? Do you agree? And now it's up to you. You could define even different weights. You could say that I want this to come with weight Z, A, B, this to come with a weight Z, B, C whenever I have a propagator. You can put different weights for the contraction. It doesn't need to be 1 and 0. It can be different weights. How would you put it here? Just put it here in the matrix. Put whatever weights you want. If instead of 1, 1, you want alpha 1 minus alpha, put here alpha 1 minus alpha. Now some propagators are favored compared to others. Right? They don't need to be just 1 or 0. They can be whatever you want. Okay, that solves a more general graph problem where you weight graphs in a different way.
So where does the J and C terms of the extra terms in the exponential came from? So you got G x to the fourth.
G x to the 4th factorial plus the same thing for y plus the same thing for z. It can be the same J or not, depends. It's up to you. If you want, no. You can put GA, okay, and now x to the 4 over 4 factorial GB, z to the 4 over 4 factorial GC, okay, if you want. Now we have a vertex for A, B, and C. Right? And if the rules are like this, for example, do I need to have the same number of A, B, and C? No. Because I can have a graph, for example, where all A's connect to all B's. That's okay. That has 1A, 1B. So I can also have a graph like that, which has 1A, 1B, 1C. But I cannot have just A, because A needs to go to B. Right? So, but this solves that problem there. But then you see that you could imagine, let's do even, let me open a parenthesis here. And say, and we can pose a question. So this is a small parenthesis. We went from x to two variables, x, y, which was associated to blue and red, for example. Then we went to x, y, z. That was three types of vertices, right? The vertex A, B, and C vertices. Right? And of course, we could go on, increase more and more and more and more. And suppose we increase it to infinity. And I want to increase it to infinity to think like this. I want to think that now I have a variable, and I will change letter from x. I will call it psi, because it's fancier. And the indices I will call P1. And I have all the way to P infinity. There are infinitely many. Where this is a point in space-time. So for each point of space-time, I have a variable psi. If you want to make it finite, just put a grid, a very thin grid. Then you have a million points rather than infinite, okay, in this room. So put 1 point, each point here in a grid, you call it P1, P2, P3, P4, P5, and you have one variable for each point. Okay? Is it okay? Okay, good. And then, instead of just x cubed plus y cubed, like we had before, now it would be a summation over all points of space-time, psi associated to that point, cube psi. Okay. And then, instead of a propagator, now the propagator would be a propagator that would say that there is a two-point function between a point of space-time P1 and a point P2 that I want to interpret as saying that I have a point P1 of space-time. There are many points. But I'm considering the propagation between these two, say P1 and P2. And I want to say that this describes the propagation, or the probability of propagation, of a particle from point P1 to P2. I have some probability of particle going from 1 to 2. Right? But then see, what are we doing here? We are saying that here I have, let's put a coupling here, I have with some probability g a possibility of the particle splitting into two. Right? And then the particle also can propagate from P1 from P2. And then our partition function Z would be also a picture like this, where I would sum over all possible terms like this, plus, etc. But what does this mean now? This means that I take any point P in space-time. Here I take any other point P prime in space-time, and I sum over all possible points in space-time connected by a propagator. Right? And to describe propagation of particles, I would start with a particle, it goes to any other point, it splits, it goes, and I sum over all these possibilities. Okay? So this is what is quantum field theory. Okay? So quantum field theory, we could start formulating it now by saying I want to decorate these graphs by points in space-time, particles propagating, splitting. The splitting represents the interactions. And the graphs that you were seeing yesterday in Tiago's lecture when he was drawing these lines and exchanging particles are exactly just this. They are exactly representing that I have now a model where I have one field for each point of space-time. Right? So that's how this will be like the beginning of quantum field theory. Okay? So that's just a parenthesis to say that quantum field theory, the difference between quantum field theory and these graphs is that in the graphs, there's no notion of space-time. So it's like if you have just red and blue, it's like there are 2 points in space-time. You are either in red or in blue. So it's a space-time with 2 points. But instead of red and blue, you have a label for each point. Now you start to describe you can describe some geometry, like some space-time. Okay? And then you have a field, and then this is called a field that depends on the space-time position. Okay? And this describes this field splitting into two, going, and so on. That's a particle. And if you have more than one type of particles, well, then you need more variables. You need one field for the electron, one field for the photon, if you want to have rules where the vertices have those. And those are the kind of diagrams that Tiago was drawing yesterday, where he had the electron and the photon. You could now easily generate some Gaussian integral with the appropriate vertices that would generate those interactions. Okay? So that's just to give you a small flavor of how that would go. But this is just a parenthesis. For now, we stay with our graphs where space-time is either red or blue. There are only 2 points. In particular, because we are doing these graphs, I want to just mention something very basic, that there is no notion of points being close or not, because the point is either red or blue. Or in the case of just a single field, it is just a vertex. There's no difference. When I have a complicated graph, like say a graph like this, right? You could say that this point is far from this, but okay, as soon as I have, say, a connection like this, I mean, now they are not far, right? I can just redraw the graph and put this point close here and this point far away. There is no notion, really, of who is close to who. I can even have lines like this, lines like this. There is no natural notion of distance, or even of being close versus far when I draw in a graph. So it's not 100% true. I could define something. I could say, if I have a very complicated graph, 2 points, there is a minimum number of steps to go from one to the other. That I could still define some kind of distance. But because a graph doesn't have a definite dimension, definite way of embedding, it's harder to think of of saying this region is far from this region, and so on. So there is some notion of distance, but now suppose we go from this, which is a graph, to what is called a map. And the map is a graph on a surface. That is, it's a graph that I draw on the surface, on some surface, without lifting the pen. I don't allow this in a graph. In a graph, the line cannot just go below. This is not being drawn on a surface. It's like you have to draw without lifting the pen. Okay? Graph on a surface without lifting the pen. Okay? So for example, this okay? So this would be what we would call a planar graph. But by using planar graph or planar map. In the sense that this I could draw on the plane without lifting the pen. It has a bunch of cubic vertices. It has a quartic vertex. Right? So this one is quartic. Most of them, the ones I drew, they are almost all cubic. We could also add something a little bit more. That one is quintic. And that's a planar graph. And planar stands because it can be drawn on a plane or sphere. Sphere, why? Because if I have a plane, I can just add the point at infinity. Now it's a sphere. So if I can draw on a plane, I can draw on the sphere. It's the same thing. Right? The sphere is just a compactification of a plane. Okay? And now, in this graph, so if I have a very complicated graph, I cannot stop drawing it, right? It's so much fun. Now, because I'm drawing it on a plane, if I have a huge graph with a million stuff, for sure, this region, I can say, is far from this region here. Right? Because I'm drawing it on a plane. It really, there starts to be a notion of close by regions and far away regions, right? Everyone would agree that this region here is far from that region there, right? Because now I cannot just reshuffle things. I cannot lift the pen. So there starts to be some notion of A and B, and A is far from B. Okay? And so these improved graphs, which are maps, right, start to be more relevant if I want to describe some kind of random surface. From far away, this looks like a discretization of a surface, right? If I have a million vertices instead of 20 like I drew, right? I could continue a bit more, as you can imagine, but then it starts to look like a discretization of a surface, right? So if our goal is to go towards surfaces, what we want is these maps, which are graphs on a surface without lifting the pen. And that's where we are going to turn in the afternoon. But before doing that, I owe you the computation of Z without source, right? You didn't complain. It's not so crucial. But just to close this subject, let's just compute Z of 0. So, and it's very simple. You just say that this is integral dx1 dxn exponential of minus x dot a dot x over 2. Right? But this matrix A is symmetric, so it can be diagonalized. Right? So I can write this matrix A as A1 up to AN, zeros here, times some diagonalization matrix, say U minus 1. U is just a rotation matrix, right? And therefore, this full object becomes U times X and because it's just a rotation, this U minus 1 is equal to U transpose. And so this is just U dot X transpose. And therefore, we see that if I call this rotated variable y, then this integral becomes the integral dy1 dot 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 dyn. Let me emphasize that there's no Jacobian because this is just a rotation. Rotations don't carry Jacobians, right? We are not stretching anything. We are just rotating to a good basis. But now the integral decoupled because it became e to the minus a1 y1 square over 2 minus dot 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 minus yn square an over 2. And each of these integrals over y1, y2, y3, yn we know how to do, right? It is just a one-dimensional integral. So each of them gives square root of 2 pi over aj, and we have product from j equal to 1 up to n. So we get 2 pi to the power n over 2. And now I have product of eigenvalues of matrix. But what is the product over the eigenvalues of the matrix? That's the determinant of the matrix. Right? So I don't need to diagonalize. If I have a matrix, just compute its determinant. And it is just divided by the square root of the determinant of the matrix A. Right? So we diagonalized for the intermediate computation, and then we covariantize. We saw that instead of computing eigenvalues, it's better just compute the determinant. It's much faster at the end. Right? So it's like pick a reference frame where it's diagonal, compute, and make it covariant again. Yeah, so that's the result for z of 0. So z of 0 is equal to this expression here.
What happens if one eigenvalue is 0?
So if one eigenvalue is 0, it means that after you diagonalize, the integral over, say, y1, here I have 0, right? So the integral is infinite. Because there is one direction where nothing depends on it, and you are integrating from minus to plus infinity. So for the integral to be finite, all eigenvalues cannot be 0. If the eigenvalue is 0, the result is infinite, and indeed, determinant of a matrix which has a 0 eigenvalue gives 0, so 1 over 0 is infinite. So it just diverges, right? It just means that you are not integrating a Gaussian. You have a Gaussian in one direction, and in the other direction is flat. So you are computing the area below a dome that goes to infinity in this direction, so that's infinite, right? So you have to make sure it's a Gaussian in all directions. So all eigenvalues better be positive, indicating that it decays in all directions. Right? Okay, so we'll stop here. So in the next lecture in the afternoon, the idea is to see. So now we are specialists in graphs. We would like to be specialists in maps. And we have to see now how do we go this step further and go now from graphs to maps. Okay? So that's what we start doing next time.
Is there an easy way to see if a graph can be written in a surface or not?
Yes.
Based only on the relations between the...
There is. I will explain that, yeah.
More question.
Uh-huh.
I don't understand what you mean by a planar map. Isn't it on the surface already?
Yes, but surfaces don't need to be a planes. You can have donuts, for example. Donuts, they have genus 1. So there are different surfaces of different topology. The simplest topology is the plane or the sphere. That's one type of surface. And that's the same. They are called genus 0 surfaces. But then they have higher genus surfaces. So higher genus surfaces then would lead to higher genus maps.
Okay. And you call those maps in the same way you call like functions maps, where you map. What's the meaning of the name map? Like.
It's a good question. Why? What could it be? Maybe it's because since they can be drawn on a surface, it's like a picture of roads on a map.
With graphs, or also like
But graphs, it doesn't look like a map. If you connect New York
you mean
to Sao
literally a map.
Paulo.
Okay.